Welcome to the next lesson where we continue our analysis of finding equilibrium in two and three-dimensional objects. So today what I would like to do is to um, introduce to you a shortcut approach to finding the forces and moments when you're solving for equilibrium problems in rigid bodies. So we'll talk about a two-force and a three-force body, and then we'll solve one example problem to show you how to apply these techniques. So remember that so far, in order for a rigid body to be in equilibrium, uh, you must make sure that the body is not translating or rotating under the given loads, right? And so when you set up your equations, the idea is that the net force is going to be zero and the net moment about any given point should also be zero. So let's look at this situation here where we look at a body on which there are only two forces acting, or rather, the better way to think about it is that you have a rigid body that is subject to forces that are only acting at 2 points. So, for example, you look at this frame here, it's called a corner frame, and we have forces F1 and F2, and they're acting at 2 points on this body. Such a situation is called a body under two force condition. Okay? Now, a question for us is, we know that equilibrium requires that the net force and the net moment about any given point be zero. And we can go ahead and always solve our problem by using those conditions, right? So net moment about some point is zero, net force about, or the total force acting on the body is zero. Now it turns out that if we think about what the consequences of these two equations are in the situation shown here, we'll see that of the three conditions A, B, and C that are shown, it turns out that condition C, where the two forces, of course, they have to have the same magnitude and they have to be pointing in opposite directions, and finally, they have to have the same line of action. So for a two-force system, these three conditions allow you to basically satisfy the requirements to achieve equilibrium. That means net moment about a point is zero and the net force sums to zero. Okay, so just keep this in mind, because when you start solving complex problems that involve members or parts which are subject to two forces, like shown here, or forces only act at 2 points, as shown here, then you can immediately realize that in order for that to be in equilibrium, the forces need to be behaving in this manner shown in figure C here. Okay. Now let's think about a second situation, and this is called a three-force body, right? And just like in the two-force case, there were forces acting at 2 points in the body. The three-force case is that the body is subject to forces acting at only 3 points. And the situation is shown right here, where we have F1, F2, and F3 acting at points A, B, and C. Once again, we can go ahead and do our traditional analysis, write down all the moments, add up all the forces, and see that the sum of the moments is zero about any given point, and the net force also sums to zero. But a deeper analysis will show you that the situation shown in condition C here is the one that will lead to equilibrium. And what that is saying is that essentially the forces are concurrent. That means they all pass through the same point when they are extended along the line of action. So in this case, for example, point D is where all three forces are passing through. And if the forces do pass through that, then you're going to have equilibrium. So one condition is that the line of action of all the forces should be concurrent. It also turns out for the three-force system that the forces can also have a parallel line of action. Okay, so that's the other condition that is required. So if you achieve one of these two conditions, either forces are concurrent or the lines of action are parallel, then you can have equilibrium in a three-force body. Yeah. Okay, so with that, let's apply this idea to one example problem to see how you can simplify the situation. So here's the problem. We have a man who is using a rope to pull on a joist, right? And this is a joist here, and it is 4 meters long. And the problem asks you to first find out whether the joist is under a 2-force or 3-force condition. Okay, so that means are there forces acting at 2 points or at 3 points, and then also to find the tension in the rope T. Okay, so obviously this is a rope here. You find the tension in that. As like other problems, we are going to use the smart approach or a smart strategy to understand and solve this problem, right? So as in terms of the strategy, our first step, as is always the case, is to draw the free body diagram. And this is a two-dimensional problem. We draw the free body diagram of the joist and show all the forces on it. And if we can find all the forces and locate where they're acting, then we can determine whether it's a 2-force or a 3-force system or condition rather, right? Okay, so let's go ahead and draw the free body diagram. So shown here is the FBD. So at point B, I have the tension T, and somewhere, since we are not given specific details about the joist, we can assume that its mass is uniform throughout its length, and that means its weight is going to act at the center of this joist. So that's what is marked out here, G. And then we have reaction force acting at point A, that's pushing on the joist. And so now when we look at this, we can see that we basically have forces acting at 3 different points, and so this is a rigid body under a 3-force condition. Now here's the analysis we can do now, um, or rather the modeling that we can do now. And the fact is that since we want to find the condition for equilibrium at this moment here, and we have a 3-force condition, in order for equilibrium to be achieved, we know that the 3 forces, their lines of action should actually meet at a specific point, right? As we noted on in the previous section for equilibrium for a 3-force condition. So what is shown in the free body diagram here is also this point C, which is where the 3 forces are, the weight W and the tension T, are meeting when you look at their line of action. Okay, so now this gives us an additional piece of information, because now we know that there is a point C here where the 3 forces are meeting. And now let's go ahead and see if we can figure out where that point C is and solve for the problem. Okay, so that's what we're going to do here. So now we're going to find out this angle alpha, that is the angle at which the reaction force is acting, such that it passes through the point C. Okay, so just to make things a little bit clearer now, what we're going to do is to redraw the free body diagram in such a way that we can find out the location of C and the angle alpha through geometry and the information provided to us in the problem. So for example, we know that ABF is a right triangle with AB the hypotenuse, and that means length BF and AF can be equal if the angle is 45 degrees, and which is exactly what is given to us in the problem, right? So the angle BAF is 45, and so we know that BF equals AF. And so let's go ahead now and write down some of the other things that we can get to. So we just saw that AF equals BF, which is also AB cos 45, and similarly you can see that CD equals EF, which is going to be AE, right? And the reason for that is because G is at the midpoint of AB, and so AG cos 45 is going to be the same as GD cos 45, which is nothing but AE and EF. Okay, so that's sorted out here. And then finally we have BD, which is going to be basically CD cot 45 plus 25. So make sure you understand how that comes about. And finally, we have CE, which is the same as DF, which is nothing but the total length BF minus BD. Okay? And so that gives us all the information we need, and we can find the angle alpha to be 58.6 degrees. So now what remains is to be able to find um, the the actual force or the tension that's applied, and we can do that either using the vector approach, or we can also use that using the triangle approach, which is one of the techniques we learned way back in chapter 2. Okay, so we'll show you how to use the triangle approach here. So I've constructed the force triangle. Remember, when a system is in equilibrium, the force polygon should close onto itself. In this case, the polygon is a triangle, and you can see here I have R, I have T, and I have the resulting weight that's pointing downwards. And so this triangle must close on itself. And so once we construct the triangle, we see that we can actually use the law of sines here with T over sine 31.4 be equal to R over sine 110, which is equal to the weight divided by sine of 38.6. And so from this, we can find that our tension, the unknown value of the tension, is 81.9 newtons. Yeah? And similarly, you can find R for this triangle from this triangle approach. Okay, so the idea here is that although you could go about and use the vector approach, this method gives you an additional tool to simplify the problems, because we started by recognizing that it's a three-force condition, and so for equilibrium, the three forces, when you extend their line of action, they should all pass through the same point. Okay, okay, so with that, we end this particular topic. Please make sure to go back and read section 4.2 of the textbook to review this content again. Thank you.